To see why a look matters, we have to go back to the slit that wouldn't behave. The experiment that refused to behave. Dim the room. London, 1801. Thomas Young stretches a card with 2 slits and lets light spill through. On the wall, bright, dark, bright, interference fringes, the signature of waves. Water does it. Sound does it. Light apparently does it too. For a century, that felt settled. Then 1905, Einstein's light quanta crashed the party. In some experiments, light hits like particles, photons. 2 identities, one thing. By the 192s, the shock deepens. Electrons, the pinpricks of matter, diffract and interfere. You can feel the floor tilt. Waves and particles aren't species. They're stories hardware tells. Now it's personal. You're a grad student aligning an electron double slit. You choke the beam to a trickle, 1 electron at a time. Dots appear, lonely freckles on a phosphor screen. Come back an hour later, the freckles have conspired into stripes. No crowd behavior. Single arrivals still built interference. The line you write, each electron interferes with itself, feels like a confession, not an explanation. You push. What if you learn which slit a given electron used? You mount tiny detectors near the slits. Polarizers, beam splitters, current-sensitive wires, anything that couples enough to tag a path without a shove. The stripes vanish. The screen fills with 2 fat humps, as if you fired pellets. Turn the detectors off. Stripes return. You try gentler couplings. Still gone. The lesson bites. It isn't disturbance, it's knowability. What counts as knowing? The notebook gets messy. If a whisper electromagnetic coupling is enough, then the lab is littered with accidental observers, air molecules, thermal photons, table vibrations. Maybe looking is just the world leaving a mark, but the precision stings. With path info available, you don't get a bruised interference pattern. You get a clean sum of 2 single-slit spreads. A toggle, not a smear. You tune detector efficiency, so only some electrons are tagged. The data split like a clean coin. Events with path info contribute to humps. Events without path info contribute to fringes. Fractions match the detector's success rate. No electron both leaves a tag and helps a stripe. The categories don't mix. That sharp line nags more than any slogan about mystery. Meanwhile, the literature piles on. Photons, electrons, neutrons, even C60 buckyballs. Untouched, they build fringes. Leave which path information in principle, fringes die. In principle sounds philosophical until you breathe wrong. One night you forget to pump down. Morning gauge reads high and the stripes are gone. You exhale near the beam line and watch visibility sag. Air is a measuring device with no display. Scattered molecules entangle with the path. No person learns anything. The possibility that a record could exist is enough. You test polarization. Put identical polarizers before both slits. Interference lives. Rotate one by 90 degrees. Each path now carries a different polarization label. Interference dies. Add a downstream analyzer that erases the difference. Mix the alternatives back into indistinguishable states, and the fringes return inside the properly sorted subset. On the raw screen, still humps. In the coincidences that respect your eraser, stripes bloom. You didn't repair damage, you removed the label. Coherence becomes the word you circle. It's the quiet phase relationship between alternatives that lets amplitudes add and cancel. Detectors don't just sense, they correlate. They entangle the electron's path with another system, a tag. When tag states differ, the full quantum state holds the paths on separate ledgers. Cross terms don't contribute because the math respects the bookkeeping. Add amplitudes when histories are indistinguishable. Add probabilities when they're not. You rewrite your language. Instead of, the electron is a wave, you say. The state evolves along alternatives whose amplitudes can interfere if nothing correlates those alternatives with readable marks. Instead of, we looked, so it chose, you say, we created correlations that made the alternatives distinguishable, so interference terms can't contribute. The story feels colder and cleaner, but one bruise remains. Even with the logic of labels, why does any single dot hit exactly where it hits? Why that bright fringe, not the dark?
Next to it, the equations give distributions. The lab gives a point. You stare at a spec and write what every physicist writes at 1 a.m. When does possibility become fact? The next afternoon, your mentor drops a thin paper on the bench. John Wheeler's delayed choice. Build an interferometer that lets you decide wave-like or particle-like behavior after the photon is already committed to both paths. It reads like a dare. If causality is safe, timing won't matter. If our questions retroactively shape what the past even means, you'll feel it.
You glance from the beam line to the clock and feel the floor tilt again. Hidden in your margin is a warning you won't forget. Language will try to run the show. It'll say the particle knew, or you changed the past. The apparatus will say something stricter. Your design decides which correlations exist, therefore which stories your data can support. And the next experiment will ask whether that choice can arrive last. Delayed choice, messing with causality. Wheeler's dare starts with cleaner plumbing. Trade the slits for a Mach-Zehnder interferometer. 150 beam splitter launches a photon into two paths at once. Mirrors steer them. A second beam splitter either recombines them to make interference or, if removed, keeps them separate so each path maps to its own detector. With the second splitter in, one detector goes bright, the other dark, depending on path length difference. Pull it out and click split, like you had tiny bullets picking one arm. Now twist the knife. Decide whether that second splitter is present after the photon has already passed the first splitter. Put an electro-optic switch in the recombination region. Drive it with a fast, random signal, cosmic photons, a high-speed QRNG, so the choice happens at the last microseconds, space-like separated from the source. You promise yourself you won't let language cheat. No, it knew. Just apparatus and timing. Run it live. When the second splitter is inserted, the dark port stays quiet and the bright port fires, just as if the photon traveled both paths and recombined. When it's yanked out, clicks show up at both ports with probabilities set by which path was taken. The surprise isn't the patterns, you predicted those. It's their obedience to a decision made too late to feel comfortable. Your last second switch lines up with whether the earlier segment is even describable as wave-like or particle-like. It lands like an accusation. What did the photon do before you chose? Here's the restraint the apparatus demands. You didn't change the past. No record existed of a path before your choice. No film reel was rewritten. What you changed was the joint question the whole experiment asks. With the second splitter in, you ask the world to reveal interference between two indistinguishable histories. With it out, you ask for which path correlations. Those are different questions with different allowed answers. The data refuse to support hybrid stories. You try to outsmart the setup. Leave faint which path tags along the arms. Tiny polarization rotations, weak scatterers, too small to obliterate interference on their own. Then choose the second splitter late and see whether something earlier bleeds through. But faint tags are still tags. With the splitter end, the interference contrast drops exactly by the amount of leaked distinguishability. With it out, the which path clicks sharpen by that same amount. The trade-off tracks a number, not your schedule. Timing games don't beat Knowability's bookkeeper. You stretch the geometry to the sky. Wheeler's cosmic version uses a quasar lensed by a galaxy, two routes a galaxy apart that still meet at your telescope. Your instrument can either recombine the routes to reveal fringes or keep them separate to read which image the photon took. Your choice happens now. The light left that quasar billions of years ago. If you recombine, you see interference that depends on phase differences laid down across intergalactic distances. If you separate, you register which route. It's not that your late decision rewrote a billion-year journey. It's that the only consistent stories your data permit are the ones matched to your measurement context. Switch perspectives to keep your footing. Think amplitudes. The photon evolves along two coherent alternatives until you change the unitary map at the end. Inserting the second splitter mixes those alternatives and allows amplitudes to add. Removing, it keeps them apart, so you add probabilities. Wave and particle aren't states the photon wore. They're summaries of what the entire apparatus plus evolution asked of it. You test the firewall against paradox. Could someone stationed near the first splitter learn in real time which setting you'll pick downstream by watching local clicks or fields? No. Local statistics are blind to a distant setting. The influence shows up only in correlations revealed when both sides' data are compared.
That's the guardrail that keeps the story causal. No faster-than-light messages, no time travel hacks, just joint patterns that refuse to be classic. Labs get ruthless about the timing. Electro-optic modulators switch in nanoseconds. Random choices are generated fast and independently. Path lengths are balanced, so the photon spends as little time as possible in indecision. Space-like separation is engineered, not assumed. Papers stack up with the same verdict. Your choice sets the question. The past stays a ledger without a single narrative until the question is fixed. A human beat sneaks in. At 2 a.m., you stare at a live S-curve that flips between interference and particle-like counts as a random bit stream drives the splitter. You feel the tug to say the photon waited for you. You write a note instead. Choice selects correlators, not histories. You underline it twice. Then someone drops a rumor with teeth. Don't just choose late. Mark which path earlier, then erase that mark later after the signal photon has already hit the score again. The delayed choice quantum eraser sits there like a dare.
What if yesterday's labels can be made irrelevant tomorrow? Quantum eraser. Information is the villain. The rumor isn't hype. Scully and Drew sketch it in the early 80s. Don't kick the particle, just tag the path gently and see if the mere availability of that tag kills interference. Then later, scramble the tag so the paths become indistinguishable again and check whether fringes can reappear. Not on the wall, but hidden in carefully paired events. The villain wouldn't be force, it would be information. Kim's 1999 version turns the idea into wires and glass. Use a crystal to spit out entangled photon pairs. Call them signal and idler. Send the signal straight to a screen where it lands now. Route the idler through a maze of beam splitters and mirrors that either preserves which path labels or erases them by recombining options into the same downstream states. Critically, the idler's journey is longer. The screen dot shows up before you've decided what to do with the idler's tag. Run it, and the raw screen is a letdown. 2 bland humps, no stripes. Then you do the forbidden thing. You slice the data by coincidence. Group the signal's dots that coincided with idlers detected in the eraser outputs, where the 2 idler paths are indistinguishable at the end, and interference patterns bloom inside those subsets. 1 set of fringes in 1 eraser channel, a complementary, phase-shifted set in the other. Group the dots paired with idlers that carried which path marks and you get no fringes. Add everything together and the stripes vanish again into 2 humps. It feels like sleight of hand until you accept the rule. Interference belongs to indistinguishable histories, and coincidences are how you pick them out. The stakes are surgical. The signal photon never met a clumsy probe at the slits. All the path information lived in correlations with its idler. When the idler optics keep those correlations readable in principle, the signal's alternatives can't interfere. When the idler optics erase distinguishability by mixing the idler's path labels into the same final state, the signal's alternatives are allowed to interfere, but only inside the coincidence classes that respect that mixing. Translation: if a label could exist, your stripes die. If the label is truly gone, they can live again, but hidden in the right pairing. Language tries to run away. No, you didn't change a dot already printed on the screen. The signal hit before the idler even finished the maze. No message rides backward in time, and nobody. It's the cleanest way to ask a precise question. Among the events where the idler left no readable path label, do the signal's alternatives show phase-sensitive addition? The answer is yes. Every time you built that indistinguishability honestly. Push the dial to partial marks. Rotate polarizers by a few degrees, so the idler's 2 path states aren't orthogonal, or tweak beam splitter ratio so tags are only partly readable. The contrast of recovered fringes slides continuously with how overlapping the idler states are. Full path knowledge kills interference. Partial knowledge dims it. Full erasure recovers only the fraction you truly erased. Beneath the lab notes runs a compact law. Visibility squared plus which path predictability squared stays bounded by 1. A human beat cuts the jargon. The first time you see fringes appear only after a database sort, your stomach drops. You scramble to rule out bias. You shuffle time tags. You flip labels. The eraser coincidences keep their stripes. The which path coincidences stay smooth. Add them together. The stripes.
Cancel. The universe refuses to give you interference for free in totals. It doles it out only inside the questions you earned. So what exactly got erased? Not a scratch on a track. What was erased was the possibility, even in principle, of telling which alternative occurred. In the eraser arms, the idler's 2 potential markers are transformed into the same downstream state. So the full entangled state no longer carries a label that keeps the signal's alternatives on separate ledgers. When labels match, amplitudes add. When labels differ, probabilities add. The screen's dot is part of a 2-photon sentence either way. Don't forget the guardrail. None of this enables faster than light communication. The screen alone is always boring. Only joint comparisons reveal fringes, and those comparisons require classical coordination. The no signaling rule stays intact because local marginals don't budge with your distant eraser choice. Then the villain grows fangs. Replace controlled optics with the room. 1 stray scattered photon can carry a path label into modes you'll never see. If in principle, you could catch that photon and interfere it, you can design an eraser and resurrect stripes and coincidences. If the label disperses into countless thermal modes, the door slams. Decoherence spreads, which path information so widely that erasure becomes astronomically impractical. The environment is a giant which path detector with no readout and no undo. This is the edge where the story sharpens. The double slit's mood swings aren't about conscious attention.
They're about correlations that make alternatives distinguishable. The eraser isn't forgiveness, it's accounting, removing labels so histories can mix again. You start to see measurement not as a magical event, but as a coupling choice. Build tags and you get facts. Starve tags and you get stripes. But that leaves a sore question staring back from a single dot. If measurement is entangling and decoherence is environmental bookkeeping, when exactly does a maybe become a fact? To chase that, you have to ask what a measurement really is. What counts as a measurement, really? We've been blaming information. Now we have to say what kind of information turns a maybe into a mark you'd bet rent on. 3 moves wear the same lab coat but don't do the same job: entangling, decohering, and measuring. If we mix them up, we'll keep mistaking bookkeeping for magic. Start with entangling. Any gentle coupling that correlates the system with something else builds a joint state. Before the coupling, an electron's 2 paths are coherent alternatives. After a path tag, the world looks like this in words: left path with left tag plus right path with right tag. That superposition didn't disappear, it spread. Nothing has collapsed. You simply copied which alternative into a second system, even if that system is one spare photon or a current in a wire. Now watch what the tag does next. It leaks. The tag bumps air, shakes the mount, radiates a little heat, scatters stray light. Tiny couplings that multiply. Mathematically, if you refuse to keep track of all those degrees of freedom, the off-diagonal terms, the quiet phase relations that power interference, shrink towards 0 in the state you do track. That is decoherence. Phases don't die. They get smeared across too many partners to ever be reassembled in practice. Interference becomes a museum piece unless you isolate and cool like a maniac. Measurement adds one more ingredient: amplification into a stable, redundant record. Avalanche photodiodes drive a microscopic fluctuation into a macroscopic current. Photomultipliers cascade electrons into a thud your scope can see. Cloud chambers make ionization bloom into a silver line. The device is designed to tip an unstable microstate into one of a few macrostates, then splash that result into the room as heat and scattered photons. Redundancy is the point. Many fragments of the environment now carry partial, consistent copies of the outcome. That's why lots of people can check the same dot later without erasing it. So the latter is correlate first, let the environment smear phases, then amplify and broadcast. Stir those together and you get facts in practice. But here's the hard edge. Decoherence explains why you never observe interference between macroscopically different outcomes and why classical-looking probabilities show up. It still doesn't pick which outcome becomes your experience. The full quantum state after measurement contains branches for each alternative, stripped of mutual coherence by the environment. Your notebook has one line. How do we connect those two? That's the measurement problem, and it won't be solved by swapping observation with eyeballs.
Space shrink as you dial up the coupling to a warm resistor. It's a volume slider on decoherence. No one looked. The resistor did. When you crank an amplifier and record a voltage that screams or 1, you've crossed into measurement. A robust mini-copy mark exists, whether anyone reads it now or later. The environment doesn't smear in any old basis. It picks the one your coupling keeps asking about, the pointer basis. Position is a classic because almost everything couples to where stuff is. In optics, polarization can be a pointer basis. In qubits, it's often energy or the computational states your readout prefers. The environment keeps hammering the same question over and over. Where are you? States that answer in that language resist further spreading. Coherence between them dies fastest. That's why chairs don't smear and why a dust grain's position gets copied into sunlight and air from every angle. This is where objectivity sneaks in without metaphysics. Quantum Darwinism says outcomes become objective when many independent environment fragments carry the same record. Photons bouncing off a grain each hold a bit of its position. Different observers sample different fragments and agree because they're reading the same redundantly stored fact. That agreement doesn't need a single cosmic ledger. It needs lots of overlapping ledgers that match. If that's a measurement, where's collapse? Depends on your taste. Many World says there's no extra ingredient. All branches persist, walled off by decoherence, and your sense of chance is self-location inside one branch. Objective collapse says nature sprinkles real, random jumps. Rare for small systems, common for big ones, on top of unitary evolution. The jump makes the pick. Copenhagen keeps the focus on practice. The cut between system and apparatus marks where we apply the probability rule and update the state as a tool. Cubism moves the update into the agent's head. A measurement is an act, an outcome is an experience, and the quantum state encodes personal bets constrained by the Born rule.
Bohm hands you definite particle positions guided by a wave. The apparatus funnels the guiding wave into non-overlapping packets, and the particle rides one, giving you a definite record. Labs don't wait for a referee. They engineer which basis gets monitored, which channels get suppressed, and how fast redundancy grows. Error-correcting codes are industrial quantum erasers. Measure syndromes that reveal which labels leaked without learning the data's value. Then repair before visibility dies. Weak measurements peck at a system, pulling out partial information while leaving enough coherence for second acts. Quantum non-demolition readouts choose observables that commute with what you'll ask later, dodging fresh labels. A small human moment pins it down. You're aligning a camera on a single photon source. The counts look jumpy. You slide in a neutral density filter to test for saturation and watch the count statistics change shape from Poisson-like to something with fat tails. The filter added nothing mystical. It changed the chain. Correlations, leakage, amplification. Your log reads, new pointer, new records. It's dry. It's the truth. So what counts as a measurement? Any coupling that drives a microscopic variable into a macroscopic redundant record in some pointer basis, with decoherence making reversal hopeless in practice. Your eyes aren't special. Your retina is a warm detector array, plugged into a brain that updates beliefs after the room has already written the outcome everywhere. That leaves one open loop we can't dodge. If the world can smear possibilities into classical-looking spreads without picking, who or what picks the line your notebook ends up with? The fight over that question isn't in the optics. It's in the interpretations waiting outside the lab door.
The big interpretations cage match. The lab gives you two rails: smooth unitary evolution that spreads possibilities, and blunt, definite outcomes that show up as dots and clicks. The math is one line. Your notebook is one line. Bridging them isn't a calculation. It's a choice about what you think those symbols stand for. 5 camps walk into the ring and promise the bridge in different voices. Copenhagen steps forward like a seasoned engineer. Use the quantum state to compute odds for outcomes given the setup you built. When the apparatus counts, update the state, collapse, as a rule for making the next prediction. Don't turn the wave function into furniture. It's a tool tied to the context. The cut between system and apparatus is where the probability rule bites, not a metaphysical border. Strength: ruthless focus on what experiments ask and answer. Weakness: where's the cut exactly, and why this outcome instead of that? Copenhagen shrugs and says physics is about what we can say about experiments, not about hidden machinery you can't probe. Many worlds refuses the cut. The wave function is the furniture, everything, and it evolves unitarily, always. Measurement is just entanglement plus decoherence. Branches split when the environment kills coherence between macroscopically distinct alternatives. Each branch contains a definite outcome. You never see crosstalk because decoherence quarantines branches like soundproof rooms. Upside: no special rules for measurement, no vagueness, elegant continuity from micro to macro. Cost: probability. If all outcomes occur, why should squared amplitudes feel like odds? Advocates say rational agents inside branches should weight bets by squared amplitude. Critics say that sneaks the rule in. Existential price tag: an immense multiplicity you never sample directly. Cubism pulls out a notebook and moves the whole game to the agent. A quantum state encodes your personal betting commitments about experiences you'll have when you take actions on a system. Measurement is an action. An outcome is an experience. Updating the state is updating your beliefs given new experience. The Born rule is a normative constraint, not a physical law about waves and stuff. Beauty: it dissolves Wigner's friend friction. Wigner and the friend can hold different states for the same lab without contradiction, because states are about their different bets. Rub: some want a story about what exists independently of any agent's beliefs. Cubism won't deliver that. Bohmian mechanics puts particles back on the table. The Beebles are positions that always exist. A pilot wave, the wave function, lives on configuration space and guides those positions by a deterministic equation. In a double slit, the particle goes through one slit, while the full pilot wave passes through both and steers the trajectory into fringes. Measurement is just the apparatus becoming entangled. The guiding wave splits into non-overlapping packets. The particle rides one packet, giving a definite record. No measurement problem, only dynamics. Price: non-locality is baked in. The guiding equation depends on distant settings instantly. Bell already told you some non-locality is unavoidable. Reconciling Bohm with relativity is hard work, but ongoing.
Objective collapse adds a new term to the law. Grashcake and its cousins stipulate random, rare collapses that hit more often as systems grow big. Microscopic superpositions can live long. Macroscopic ones die fast. Penrose and Diósi flirt with gravity as the trigger. Superposed mass means fuzzy space-time. Nature picks one branch in a time set by gravitational self-energy. Payoff: a clear mechanism that chooses a single outcome, and predictions that, in principle, deviate from pure unitary evolution. Cost: you must fix collapse rates and length scales, guard energy bookkeeping, and face experiments that keep squeezing the allowed parameter space. Where do they stand in your lab? Copenhagen speaks the dialect of daily practice. Define the question, compute odds, update, move on. Many Worlds explains why decoherence makes macroscopic facts robust and why interference vanishes in practice without any extra jump. Cubism tells you why different observers can carry different state assignments until they compare notes, and why that is an inconsistency. Bohm draws the flow field you see hinted at in weak measurement streamlines and lets you picture dots as guided rather than born. Collapse theories tell you why your cloud chamber tracks look classical, even if you isolated everything. Nature's stochastic tap ensures it. Stress tests with the stories we've already lived. Delayed choice? Copenhagen? The question changes at the end, so the state you use changes. No paradox. Many worlds, branches are fixed by the whole unitary evolution. Your late choice picks which basis reveals which branch structure. Cubism. You alter your bets at the moment you act. The timing lives in your ledger, not in the world's past. Bohm, the pilot.
Wave's global shape depends on the full setup. The particle's path reflects that without time travel. Collapse. If a real collapse occurred early, later recombination is already off the table. Eraser. Copenhagen. Erase distinguishability and interference can show in the right coincidences. Many worlds. Post-selection picks subbranches where phases line up. Cubism. Conditionalize on the idler outcome and your updated beliefs show fringes. Erase restores overlap of guiding waves in configuration space. Conditioned trajectories show fringe structure. Collapse. If spontaneous hits didn't happen, erasure logic holds. If they did, coherence is gone. Bell. Copenhagen keeps it operational. Quantum predictions beat local realist bounds. No signaling survives. Many worlds points to global entanglement structure. No spooky influence inside a single space-time branch, just correlations written in the wave function. Bohm nods. Non-local pilot wave guidance is the mechanism. Still no messages faster than light. Cubism says agents must structure expectations to match those correlations. The impossibility of signaling remains a rule about what any one agent can do. Collapse models typically inherit non-local features to match the data. A microbeat from the hallway. Two grad students argue at a whiteboard at midnight. One draws branching trees, the other draws pilot wave streamlines. They're talking about the same counts on the same scope. The debate trims how they think, not what they measure next morning. Here's the through line that keeps your hand steady. The lab never demanded a final metaphysics to work. It demanded discipline about questions, couplings, and records. Interpretations shape how you sleep and which paradox you pick fights with. But the devices sing the same tune. Preserve indistinguishability for stripes. Build redundancy for facts. If one day a levitated nanosphere fringes where collapse said it shouldn't, or decoherence breaks where it shouldn't, the cage match will end with data. Until then, pick the story that keeps you honest and keeps your screws tight. Wigner's friend, whose reality is real.